Okay, so 2.1 was area between curves. So to give you, I'm not going to like re-lecture this. You guys did the homework, you know area between curves. But some of the important takeaways in the area between curves section was when I'm looking at two curves, right? Okay, and so maybe I'm looking at some region inside that I want to find the area of. One of the things you talked about was we can either set this up where my area is rectangles set up, down, or I could have a situation where I would want to set up the rectangles left, right. Right? So maybe I have like a sideways parabola or something like that. Oh, that one looks worse than the first one. There we go. So maybe I have a sideways parabola, right? Like a line coming through it. And I want to find the area in between these two. Okay, in this case, up and down would present a little bit of a problem, right? I'd have the function over itself, and it doesn't make a lot of sense. But if I set up my little rectangles going left, right, then that makes more sense. It's a little bit easier. It just means that I have to integrate with respect to a different variable, right? So for this first one, my area is going to be the integral from a to b of my top function f minus my bottom function g. Oops. And I'm integrating dx, right? For the second one, if I think of this as x equals a function of y, and this one on the left as being x is a different function of y, okay, then my integral is, still between some limits of integration, except instead of being x values, these are going to be y values. And I'm going to integrate, instead of the top minus the bottom, I'm going to integrate the right function minus the left function. Okay. And so one of the big takeaways for this was I can not only find area, but I can set up integrals different ways, right? I can integrate dx or dy, whichever one is more convenient for the problem that I'm looking at. Okay, when we go on to other sections, that starts to become important, and we take advantage of that. So that's the piece of 2.1 that we really want to carry forward. Okay, so in 2.2, we start looking at volume. And what I want to do is start by just giving you an overview of how the volume integrals are set up, right? So we start with volume by slicing, and that's actually what I think is kind of like the hardest volume. The solid of revolutions, right? When I rotate around, they give us some structure so we can actually simplify things a little bit. But volume by slicing is just a generic way to find volume, right? So we take some three-dimensional object, right? And we say, maybe I have like a horn or something like that, and I want to find its volume. And what we do is we say, okay, just like in area, we broke it up by slicing it into rectangles. Here we're going to take slices, right? And if I pull that slice out, right, it's some piece that has a tiny little bit of thickness to it, right? Delta x. And so that piece by itself, if the piece is small enough, I can approximate it. Instead of following the curve, I can just use a straight line, and so I get a nice cylinder instead of a curvy shape. And so then the volume is just going to be the area of the front times that delta x. So then if I want the volume of the whole object, what I do is I say, all right, let's add up all of those slices, and each one of those had some area function times delta x. And if I want to get the exact volume, then I need to take a limit as the number of slices goes to infinity, just like we did with area in Calculus 1. And now this limit of a sum is exactly what we had from Calculus 1. That's how we defined the definite integral. We take the limit of a sum of a function delta x, we get the integral of that function dx. Okay, So that's where our integral comes from in that volume by slicing. It's by adding up these pieces. Okay, so we integrate the area function, and the way that we had to set up those problems was we had to figure out what is that area function, right? If our cross sections are circles, then I can use the circle, and I just have to find a formula for its radius, maybe. If the cross sections were triangles, right, then I have to say, all right, well, what's the area of a triangle, right? Half base times height, and then I need to find a way to write the base and the height as a function of x as x moves along. All right, then we said, all right, let's look at volumes by the disk washer method. So, all right. So the idea behind the disk method was, instead of taking any generic three-dimensional object, what we're going to do is we're going to start with something in 2 dimensions bounded between 2 curves. So like a y equals f of x and a y equals g of x. And we're going to say, all right, take that inside part and rotate it about an axis. Okay. Now, I said the disk method, but I'm kind of jumping straight into the washer method. So maybe I should let me slow that down a little bit. Let's start by we'll start with just the disk, right? Okay. All right, and the idea here is that if I look at one rectangle that would be used to find area, okay, when I rotate that around, that will give me this disk. Where the radius is exactly equal to the function height, okay? And so my area function, the area of a cylinder, right? Because in a way this is a cylinder because it's 3 dimensions. Okay, I have the front face, which is 2 pi r times the thickness, which is delta x. Okay, and if my r is just a function height, then I get 2 pi f of x times delta x. So if I want to add up all of these disks, right, I'm going to use a sum from 1 to n, 2 pi f of x delta x. To find the exact volume, we throw a limit on the front. So now, just like we had a minute ago, I have the limit of a sum, and that will give me a 2 pi r squared. Not 2 pi. See, I'm jumping ahead of myself. It's just pi r squared. Okay. All right, so the limit of a sum of a function, delta x, gives me an integral dx, right? So we have the integral from a to b of pi times my function squared dx, right? And that's where that disk method comes from. The washer method is the exact same thing, except my radius doesn't necessarily come all the way down to the axis of rotation, so that I might have a gap. And if I have a gap, then I won't get a disk. I'll have a disk with a hole in the middle, and that's the washer method. Okay, and that's why we subtract on the inside, inside our integral. Okay, so again, what I want you to pick up from this, from the big picture idea, is that we're finding volumes by breaking this down into a simpler thing, right, which is area, and then adding up all of these pieces. And so if I add a bunch of things up, that gives me an approximation. If I take a limit as the things I'm adding up goes to infinity, then it becomes an exact, it exactly solves my problem, but it also gives me an integral. So what we're effectively doing is we're building integrals that solve our problems. Okay. So let's jump now to 2.3, the shell method. And it's the same idea. I'm going to have this region that we're rotating. Okay, so once again, maybe I have 2 functions. Okay. but maybe I'm rotating about the y-axis instead of the x-axis. I still want to have my rectangles going up and down. But now when I rotate them, I won't get the same type of shape. I won't get this disc. I'll get this shell. Okay. I kind of made it a little extra big. And there's a lot of detail here that I'm going to skip over for now because I'm not lecturing this fresh or anything like that. But the idea is that I can think of this as an outside cylinder minus an inside cylinder. The outside cylinder has some radius, and the inside cylinder has a different radius. But that difference is r delta x. So that difference is really small. And that radius is going to be approximately what x is. Okay. So what we can do is we can say, well, if I go to the middle of my approximating rectangle and call that x, then that's like the average of the two radii here. And so that works out neatly in our formula, right? So that's where this x comes from, okay? And then I have a height. I'll call that h of x. Okay. So typically the volume of a cylinder, right? Well, here's a way to think about this. If I take this object that I just created and I make a cut in it, suppose I cut it right here, and I unravel it, then what I'm going to get is almost a box. Okay. Now it's not perfectly a box because if you unroll it flat, it's not going to lie perfectly flat if it has thickness to it. But if it's really thin, then it will. Okay. So what we do is we approximate it by saying it can lie perfectly flat, where this thickness here is delta x. And now when I unroll it, this length here is the circumference of the circle. Okay. And this height here is the height h of x. Okay. So we just said that the radius r is x. So my circumference is 2 pi x. And then I have my height h of x. So when I set up my volume, I have 2 pi x h of x. And that's for each one of my shells that I create. So I add those up. And then we take a limit as the number of things that I'm adding up goes to infinity so that it's nice and exact. And that's where our integral comes from. Now I'm taking the limit of a sum of some big function. Oops, I forgot my delta x because that's the thickness. So now I get my integral from a to b, and we get 2 pi x h of x dx, right? Where h is that height, so it's the difference between the two functions. So once again, I've built an integral that solves my in this case, volume problem. Okay. So that's the running theme that I want to keep in mind as we go forward, right? So I'm not going to fully lecture the remaining sections, but I want to do the same thing for the sections for this week, right? So starting with 2.4, I want to just give you kind of a big picture overview of what's going on, right? So in 2.4, what we want to do is we want to look at a piece of some curve, right? So suppose like y equals f of x, and I want to find out how long this is. Now, the first thing that we need to make sure that we understand is what is the thing that we're talking about. So like when I say area, we have an intuitive notion, but we want to make sure we're all talking about the same thing and that we've clearly defined what we're talking about. So we actually had to define area back in Calculus 1. So just to make sure that we're all on the same page, when we talk about how long is this curve, what we want to think about is if you were to lay a string exactly on top of this curve, you could stretch that string out straight, right, and measure it, and that length would be the arc length. Okay, so we can't really measure the length of a curve. What we can do is we measure distance between points, following a straight line. So what we're going to do is we're going to take this curve, right, from A to B, and we're going to break it up into pieces. And on each of the pieces, we're going to say, all right, just follow a straight line from point to point. So if I follow a straight line, I can find the length of that line segment, and I can add those up, and that approximates my area. If I use more subdivisions, I'll get a better approximation. It'll fit the curve better. And so if we use infinitely many, it'll fit it perfectly. Okay. So then what we need to do is figure out a way to find out how long each of these little segments is. And there's some algebra to that, but that's where our formula comes from for arc length. Okay. And I know that in order to find, a distance between 2 points, which is really what this arc length is, right? I need the distance formula, which is like, a piece of the Pythagorean theorem, right? So if I make a little triangle out of this, then I have a change in x, right? And a change in y. Okay. And then my distance is really, if I say that this is distance number 1, then it's, the distance 1 squared, right? If I use Pythagorean theorem, is going to be the change in x squared plus the change in y squared, right? So that distance 1 is the square root of the change in x squared plus the change in y squared. Okay, and what we do to make this work, I'm going to switch colors here because I can't really see the green. I'm sure you can't either. What we do here is we say, I'm going to factor out this delta x squared, right? So think of multiplying this second one by delta x squared over delta x squared so that I can factor one out. So I have a delta x squared, and what I'm left with if I factor out a delta x squared is 1, and if I take out a delta x squared, then I'm left with delta y squared over delta x squared. And so then this delta x squared I can pull out of the square root as just a delta x. Okay. And so that gives me my length for one piece, right? So if I want the total arc length, what I want to do is I want to add these up, and you'll see why I did that factoring here in a second, right? We have the delta x times the square root of 1 plus delta y over delta x squared. Okay. And I want to eventually take the limit as n goes to infinity, use infinitely many pieces. Okay, so now I have the limit of a sum of some function times delta x. Now here in my function, I have a delta y and a delta x, and that can get a little bit confusing, but I know what happens to those two, right? Delta y over delta x is f prime of x. So what I end up with when I get my integral is the square root of 1 plus f prime of x, which is then squared, inside my square root. Okay, so that's where my arc length formula comes from. Now when we get into this section, when I look at this, if I want to solve an integral, these are difficult integrals to solve by hand. You really need a very specific setup for this to work out neatly. Okay, so you're going to get some homework problems in this section. It feels like there's a lot of different problems, but they all fit like maybe 2 or 3 different styles of problem that you can get, right? You can get one where it just, simplifies down very nicely, or you can get ones where you can do some sort of like clever substitution thing to make it work. And we'll address that later when we go through homework questions, okay? But that's where this setup comes from, all right? But in general, that's kind of hard, and we'll talk about that later. When we get to more integration techniques, we'll be able to integrate more things. Right now, we're a little bit limited because the only integration technique you have is U substitution. And U substitution is going to be limited because I'm going to take a function, differentiate it, then square it, and add 1, and that's inside a square root. And it's like there's only so many things that a U substitution can really handle there. Okay. All right, so again, we have this idea of building an integral that solves my problem, right, by adding up pieces. We do the same thing with surface area. Right, so if I have some curve and I rotate that curve around an axis, that's going to give me you know, an object, and I can find what's the surface area of that object, right? And so to find the surface area, I can think of taking this curve, okay, and when I rotate it around, it gives me like a two-dimensional surface in 3D, and I want to find the area of that surface. Okay, and the way that we do that, the same way all of this stuff works, we break it up into pieces. On each piece, in this case, I have a line segment, and when I rotate that line segment around, that will give me a, maybe not a really nice object, but it gives me something that's at least regular. Okay, so when I rotate that around, I just took that one red piece there. That's looking terrible. Let me try that again. So if I rotate this point around, I'll get a circle. If I rotate this point around, I get a bigger circle. Okay. And so what I really get is like a cone with the pointy end chopped off. Okay. And so then we can find the area of that piece of a cone, and that's where our formula for surface area comes from. And it's a little bit more messy, right? But you know, it's because we're starting with a messy object, right? The things that I'm adding up are these not perfect cones, right? If it came out to a point, the area of a cone is already a little bit messy because I have to chop off the pointy part, right? It makes it even more complicated, but that's where surface area comes from, right? And so it's the same idea of I'm going to approximate it with a piece, and then I'm going to add those up and take a limit as n goes to infinity, and that gives me an integral. Okay, so that's section 2.4. So then in 2.5, we start to get less geometric and a little bit more abstract in a sense. Okay. So in 2.5, we're looking at physical applications, and we start with talking about things like mass, and we end up looking at work. Now, when we look at physical applications, okay, what we're doing is we're sort of laying some of the foundations for physics, and that can be a little bit challenging if you've never had physics, or you haven't had much physics, or you haven't had physics recently, or you know, whatever the case may be. Okay, so we're going to try to keep it. We're not going to go into a whole lot of depth. You don't need to understand a lot of physics to be able to do this stuff. It's sort of the other way. What we're doing is we're building a foundation that somebody could learn physics off of, right? So if you want to take physics, you know, usually they want you to take some calculus first, right? Because this gives you the foundation to build off of, okay? So when we're building stuff in our physical applications, we want to keep the same spirit alive that we were doing before, where we say, okay, the way I solve a problem is by breaking it up into little pieces, adding those pieces up, and if I take infinitely many, it will exactly solve my problem. And when I take the, you know, the limit of a sum, I get an integral. Okay. So the first thing that we're going to start with is looking at things like mass and density. Okay. So mass is just how much there is of something, and I want to draw a quick distinction between mass and weight. Mass is a measurement of how much stuff, right? So like there's a certain amount of me, and if I go up to space, there's just as much me in space as there is me on the ground, right? I haven't really changed. Okay, weight is how hard gravity pulls on me. Okay, so if I'm standing on the Earth, gravity's pulling me down. If I'm standing on the moon, it's smaller, so gravity has less of a pull on me, even though there's just as much me. So mass is how much of me there is, and weight is how hard gravity is pulling on me. Okay. The reason that this is confusing is because, like, if you want to measure yourself, right, we could say, oh, you can measure how many pounds you are. That's measuring weight. And on the same scale, it also tells you how many kilograms you are, which is not a weight, that's a mass. Okay, so the English or American system for weight is pounds. Okay, in the metric system, if I wanted to measure weight, I would use newtons, because that's a measure of force. Okay, and the metric system, if I'm measuring mass, I'm going to use kilograms. And I forget if I don't think that our book mentions the English measurement of mass. Um, there's more than one, but like I think slugs is one of them. I've never heard anyone tell me how many slugs they are. So I don't think this is very commonly used, except that if you really want to use the English system and you really want to do physics, then you end up with stuff like that. Okay, so that's just to hopefully keep you from getting confused when you start looking at units. And we're going to try to avoid things like having to do unit conversions and stuff like that. Most of our problems, all of the units are going to line up nicely, so we don't have to do conversions and things will be okay. When you're in a physics class, then you have to worry more about unit conversions, and that becomes a big deal. Okay, so density is just how much mass divided by how much volume. Okay, so if I took a like a cube of metal, oops, okay, and I took another cube made out of wood that were the same size, the metal one weighs more, it has more mass. So if I divide it by its volume, I'm going to have a higher density for a metal cube than I am of a wood cube. Okay, so that's how we can measure density. Now, if I have a material that's like consistent, right, so the mass is evenly spread out, then density is really easy. It's just a division problem. What we're going to be looking at here is what happens if the mass isn't evenly spread out, right? What if the density is different between one side and another? Now, that's not something that we, are like if you get like a cube of metal, right? Or when you look at in the book, it starts off like a rod or something like that. You don't typically get a material where the density is changing along the material. That can happen, but what you will find is, let's suppose I'm looking at an object that's heating up on one side. As something heats up, it expands, so the mass isn't changing, but the volume is, so I can change the density by heating it up. And if one side is heating up faster than the other, then the density is no longer uniform, right? So that's why it's important to study variable density, right? And that's why we start looking at this. Okay, even if it seems like it's a little bit abstract. Okay. To make things easy, we start off in like almost a one-dimensional object, right? We look at what happens if I take a really thin rod of some material, okay, where the density is changing as I move along it. Okay, so if I say, all right, let's suppose this is my x direction. Okay, maybe at any given point it has a different density. Okay. So if density is mass times volume, then I could multiply to write mass is density times volume. Okay, so if I take little slices and I know how much volume I have, I can multiply it by the density and I can get the mass. And then if I add them up, then I can get the mass of the whole object, right? And so that's kind of like where we start building up. So the mass is going to be the, let's say the density is some function, we'll say rho of x, okay? And if I'm looking at, like, you know, this thin object, right? So then I can say, my mass, I'm just going to take this rho of x and multiply it by, the thickness of that piece, okay? And we add them up, and then we take a limit on there, okay? So then we get a nice formula. Mass is the integral of density. Okay, so again, we get to this idea of building up an integral. Okay, and the way that the integral builds up sort of depends on the shape of the object, right? Because if I started with a differently shaped object, then the way that I find volume might be different, and so I might have extra pieces thrown in there. Okay, and so when we're looking at this, I don't want you to think about this section as a bunch of random formulas thrown around. I'd rather you think about this as, okay, if I start from the ground up, I have density times volume. How do I find the volume of one little piece? Okay, that's going to affect what my integral looks like, and build up from there. Okay, so we start with mass because it's simple, and then we start talking about work. Just to give you a quick overview of what work is. Again, for those of you who haven't had any physics or if it's been a while, if I hold a book over my head without moving, I'm exerting effort, but I'm not really doing any work, right? I'm not accomplishing anything, okay? But if I lift a book up off the ground and put it on the table, then I've accomplished some work, right? So let's suppose that we have a table here, and we have a book on the ground, and if we lift that book up and put it on the table, then we've done some work. Okay, if I had a really high table, I would be doing more work than if I had a really low table. So there's some work sort of measures how far I have moved this book, but it also depends on how much the book weighs. Right? If the book is really heavy, I'll be doing more work than if the book is really light. Okay, so the way we define work is we move an object by pushing on it with a force, and we cover some distance. Okay, so work is force times distance. Okay, now I say distance, we have to be a little bit careful. In physics, there's a difference between distance and displacement. Okay, so distance is how far between 2 points. Okay, displacement is the distance between where you end and where you start. Okay, and so let me just give you a quick idea. If I run around in a circle, I have 0 displacement, but I have run some distance. Okay, so if I run in a circle, my starting and ending point are the same. So strictly speaking, when we do work, we're not really using distance, we're using displacement. So if I run in a circle, I've actually done no work because I haven't really accomplished anything, even though I've exerted myself a little bit. Now, for our purposes, this is rarely going to come up. For the most part, we're just going to move in one direction and never turn around, so distance and displacement will be the same. So it's worth noting, but it's a problem that's a much bigger deal in physics, and we're not really going to address it much in our, in our analysis of work. Okay, so we're just going to look at, force times the displacement. And almost all of the work that we do, I think all of the work that well, not all of it, but most of the work that we do is going to be with gravity. So we're going to be opposing gravity. And so the force that we're doing is just, going to relate to gravity. So that's how much something weighs. And that's why we talk about mass and density first, because that gets to throw gravity in there, and then we get weight. Okay. So one last little tidbit to sort of finish off the week. 2.6 was moments and center of mass. Okay, and again, just to give you kind of an overview, we start off with a simple case, and then I'll explain why it gets complicated. Let's suppose that I have two objects, right? Two weights. And let's say one of them is bigger than the other. Okay, and they're hanging on a balance beam. Okay, then that balance beam will balance somewhere in between them, but if one weight is bigger than the other, then it's going to balance closer to that one. Okay, so that's the balancing point in between those two weights. Okay, so I could think of that as being the center of mass, right, or the center of gravity. Okay. When I take like an object that has some weight to it, right, some mass to it, I might want to chop that up into pieces. That's kind of the thing that we've been doing, right? We use these equal size pieces. So if I look at a piece and its distance from a balancing point, that gives me what we call a moment, right? So when you watch the video on this, they'll explain it in more detail, and I hesitate to write it down because it's a little bit complicated, and I don't want to oversimplify, but it's the moments are just like one piece of the system, okay? And we're trying to find the center of mass. What makes things difficult is not this thing here where I just have two objects, right? Then it's pretty easy to find the balancing point. That's effectively what like averaging is, right? So like, if I get back to Archimedes and law of the lever, the amount that this is going to pull down on my balance beam is going to be the weight times the distance from the balancing fulcrum. Okay, so if I take mass times distance, right? So suppose this has mass m1 and this is mass m2, and this is a distance d1 and this is a distance d2. Okay, this will balance if m1 times d1 equals m2 times d2. Okay, or if I want to find the balancing point, right, I want to find the point that makes this system balance, and that's effectively like taking an average. Okay. So part of finding the center of mass is essentially the same process as finding an average, where we add up these moments and we divide by the total mass of the system. Okay, so it's really the same process as averaging, where you add up and divide by how many that you have. And again, we're going to take a limit as n goes to infinity, and that's going to give us our integrals. So what we can do is we can kind of expand that onto, instead of looking at just like two objects or a bunch of objects on a balancing post, what we can do is we can expand that to saying, all right, let's suppose that I have we'll start with like a two-dimensional object. Can I find the center of mass of that object, right? If I start with something like a circle, right, a perfect circle, I won't be able to draw a perfect circle. We'll use this to draw a perfect circle. Okay. If I start with a circle, oops, that's not what I want. Right, then, I just have the center of the circle, that's going to be the center of mass. But if it's an irregular object, how do I find where that is? And that's the process of this center of mass business, where I say, okay, I'm going to do the same process that we did before with weights on a beam, except now I'm in, say, 2 dimensions. Okay. And what we're going to do is we're going to think of our objects as being really thin, because it doesn't make sense to talk about weight of a 2-dimensional object, right? It has to have 3 dimensions. It has to have some volume in order to have some weight to it. So we'll just think of it as being a really thin object, like a plate or a piece of paper or something like that. Okay. And the reason that we do that is because it's simpler, right? We start with the simple ideas and then we build on them. In this case, we won't build up to just a generic 3-dimensional object in this class because that requires more than one integral in the same problem. Okay, so that's something that you can do in Calculus 3. But we can do the first step. We can look at it. If I have these like flat objects, I can find where is that center of gravity. Right? Or as we're going to call it, the center of mass. Right? Because it doesn't really matter if you're on Earth or in space, the center of mass is the same spot. Okay, so that's just kind of giving you an overview of what we're doing here. And in the lecture videos, we'll take that out into detail and hopefully be able to solve problems. But I just want to make sure that we can, at least sort of follow along in a big picture sense. I think that we might want to have another problem day where we, sort of go over questions on problems so that we don't end up with everybody being sort of stuck on Monday at the beginning and not being able to get through things. So I think that we'll call that it for class today because we're out of time, but I'm going to maybe set something up for either Thursday or Friday to start going over homework problems just so you can get some of the initial questions out of the way and get going on things so that we don't end up fully backed up on Monday, stuck on a bunch of complicated problems. All right, so that's where we're going to be going forward. Any questions?